Hello, my name's Guy Williams. I'm an Associate Professor in Polar Oceanography at the University of Tasmania. It's my great pleasure to talk to you today about Polynyas, ice factories, and the underwater falls that kickstart the world's global ocean. I'm going to talk about a few different things today, but one of the key concepts I want to give you is the fact that the ocean, when it gets really cold and it freezes fresh. So that is, salt water freezes fresh. As the crystalline structure of the ice forming makes its lattices, the salts get pushed out, and the majority of the salts get pushed out and left behind. And they get dropped into the ocean, and what they do is they increase the density of that water. And if you make enough ice and you reject enough salt, you get this very dense water around Antarctica in very specific locations. So that's the key thing to think about. It wasn't really proven until, I guess, in the 70s by a Japanese researcher, someone I had the great fortune to study underneath at the Institute of Low Temperature Science in Hokkaido. And what we're looking at here is a Schlieren image, which is a way of looking at density variations in a transparent media. And the white line you see at the top is basically a block of ice that's frozen in seawater. And as the ice formed, salt was being rejected, and you see these plumes and filaments of salt pushing down, pouring down through the water. And I remember the professor telling me that when he saw this, he shook like a leaf. So that's the key thing. But the interesting thing is that sea ice is its own worst enemy. As you form sea ice at the surface, it cuts off the warm ocean from the freezing atmosphere above, and that slows down the growth of ice. A bit like an ice cube tray in the fridge. Once you've filled it and frozen it, that's as much ice as you're going to get. However, in certain locations around Antarctica, close to the coast, there are these persistent gravity-fed winds, and these can push the ice away that's formed. When they push the ice away that's formed, this allows the warm ocean to freeze again, forming more ice. This is like someone that diligently empties the ice cube tray every day, such that by the end of the week, you now have a huge volume of ice cubes, and that's when the party can really start. So there was a great search towards the end of the last century for these locations, areas of these strong katabatic winds, these gravity-fed winds, which are persistent and strong. And it turned out we didn't have to look too far away from home to find one. And it was right under our nose, or under our eyes, especially if we'd paid attention to the title of Sir Douglas Mawson's book, Home of the Blizzard. Turns out Commonwealth Bay, with an average wind speed of about 20 metres per second, that's average all day, every day of the year, 20 metres per second, was a perfect location for which to have a polynya over the Adélie Depression. So a polynya is a Russian word meaning open water, and in this context, it's a persistent area of open water driven by these strong winds. So again, the idea, the ice is forming and being pushed away and allowing more ice to form. So instead of just a little bit of salt, you're now getting lots of salt, and because of that, you're getting this very dense water. So I allude to the fact that 20 years ago was the first wintertime occupation of this area by an Australian expedition. And I was fortunate enough last year to go back, nearly 20 years later, to the Terra Nova Bay polynya in the Ross Sea. And this is the ship making its way into that area. It's dark. It's not actually the heart of winter, it's more autumn, but nonetheless a long night. And you can see here, these are flows of sea ice, generally together, but they're actually broken up, and you can see a long period swell. This is as we're approaching the coast. So we're probably still 10 kilometres away from the polynya, but we're noticing there's a swell being driven. This is something we normally see at the open ocean or the edge of the sea ice, but now against the coast, we're seeing this wave coming through, and that's as a result of this intense wind action. So daybreak now, we're getting a lot closer, and look at this patch, if you like, of baby pancake ice. So this is baby sea ice. Sea ice forms as small crystals that then float to the top because they're lighter. They coagulate together and form these baby pancakes. And now we're getting to the heart of the polynya. We're probably 1 or 2 kilometres from the coast, and this is hurricane strength winds. It's now 85 to 90 knots. Outside, the ship is going straight into it, and we see these waves of ice. That's not foam on the top, that's actual ice. And if you look carefully, you'll see these thin blue patches, maybe 5-10 metres below the surface. That's the fresh ice crystals that are then coming to the surface. Incredible amounts of energy being released from the ocean to the atmosphere. The little sort of back of the envelope calculations being done by the atmospheric scientists on board, who are the only people who are able to make any measurements at this point in time, was showing that maybe 1600 to 1700 watts per square metre. That's an incredible amount of energy. If you think of a general sort of household generator, it's around about 1.5 kilowatts. Imagine one of those every metre of this area of the ocean, churning away with that energy. And so really intense, probably one of the most intense and extreme environments to be on Earth, apart from perhaps the bottom of a volcano. And very special to be able to be there and witness this formation period. A lot of our observations are in summer. It's very rare for us a chance to get down there. It's only very brave captains and research scientists that can actually convince the funding agencies to get us down there. But when they do, we get this sort of condition. And so what we see there is, what we're looking at here now, is a computer simulation done by the Australian National University in Canberra. And this is a very high resolution detailed ocean model. And it's looking at the bottom layer, and in particular we're zooming in here on Terra Nova Bay, and this is the bottom layer of dense water, and you can see it coming off the continental shelf and pouring down the slope. So it leaves at about 500 metres depth and will pour down in these huge underwater falls, cascading down from 500 metres depth all the way down to the abyss at 5,000 metres. And it's doing this in maybe 3, 4, 5 locations around Antarctica. And it's these underwater waterfalls that are like the piston, if you like, for the global overturning circulation. What you might not be aware of is that the ocean is constantly moving. And it's complex, but overall, broadly speaking, we will see this large-scale transport of water at the surface moving from the equator towards the poles. In this case, we're looking at the Arctic, where it then cools and becomes dense and sinks and returns again back to the equator along the bottom of the ocean. And the same thing is happening in Antarctica. In maybe 3 or 4 locations, you can think of them as pistons. They're pumping down gases and nutrients down into the bottom layers of the ocean. And they're looking at the large-scale transport of heat and salt around the globe. And it's this circulation which is so critical to our own climate and our ecosystems. And it's being driven by this movement from the surface down into the abyss around Antarctica and to a lesser extent in the Arctic. And that's coming from these Polynyas, very discrete locations of intense wind, intense sea ice, and intense amounts of dense shelf water formation, so dense that it can move down as a big underwater fall. I'm talking 300, 400 metres thick in some places, and so critical to our life on Earth. Thank you.